Well, hello again. And so the first talk was a very high-level introduction to the AGN menagerie, types of AGNs. The second talk was black holes, a little bit about black hole physics and evidence for black holes. As we know, of course, that, or we believe that black holes exist in the nuclei of most massive galaxies, and all AGNs are powered by mass accretion of black holes. So what does that do? Well, what it does is it produces a large amount of radiation. And that radiation can ionize and, in fact, accelerate gas in the host galaxy itself. So, although there are other means that which the system can add energy to the surrounding gas, the most basic way that it works is by having the ultraviolet and X-ray photons that are produced in the accretion disk enter the gas in the host galaxy and ionize it. And that process, because of photons, is photo-ionization. So one of the most direct ways to look at the physical properties of this gas is by running photo-ionization models. All right? But first you have to have something to model. So what you really are modeling are spectroscopic data. So people use the Hubble Space Telescope, for example, and also use the Chandra X-ray Observatory and other great observatories, seem to be more successful in obtaining images. Because pictures are nice and you can do stuff with them. But to understand the physical properties of what you're looking at, you have to disperse the light and make a spectrum and see what elements or ions are there that are radiating, what the physical properties are. That tells you things like density, temperature, and things like that. You can't do that without a spectrum. So, although spectra are hard sometimes to obtain, because once you disperse the light, you have to integrate longer and longer to get good signal to noise, rather than taking an image. But once you get it, you can do a lot with it. So, the left here is a spectrum. This is actually one of mine, taken with the Hubble Space Telescope Imaging Spectrograph. ST in both ends of that acronym. This is a spectrum taken through a slit-like aperture. So what we do is we position the telescope so that slit lies on a particular part of this part of the galaxy, MC 1068, the active part, and then dispersive elements disperse the light. So in this particular case, we get a spectral image. This is a very powerful thing. So what you can see here, by the way, this thing is really bright. That's from the Earth's corona. It's geocoronal. So there's stuff in there. This is geocoronal Lyman alpha from the Earth's outer atmosphere. So very bright, but just pure contaminant. But all this other stuff, these are all emission lines of various species. I didn't label them because I can tell you what they are. Maybe. So here you've got, this is the Lyman alpha from the host. This is carbon 4. So this is triply ionized carbon. This is a helium-2 recombination line. When you look at the structure here, there's two things about it. First off, it is like little clouds or clumps. You can see that. The second thing is that it's shifted. It's not going straight up and down. This is going straight up and down because that gas isn't moving much relative to us. But here, the shifts that make the thing split like that, that's Doppler motion. And what this is the gas is coming out. I showed you a picture of that illumination cone on the first day. This is gas coming out in a cone. So some of it is blue shifted going towards you, and the other part of the cone is going into the sky, and it's red shifted going away from you. And we also see this stuff, these straight lines of emission there. That's a continuum emission. Some of it is from the AGN itself. This is a type 2 AGN, so you're not seeing the accretion disk directly, but there is some gas that's very ionized close in. And so I talked about the unified model. This is the first galaxy they understood there was a hidden AGN. And this continuum radiation is the continuum radiation produced by the accretion disk, but just a fraction of it is reflected into our view. So it's like, then And she's the mirror, the back, the bent mirror, that's what's showing that. Then, there's other stuff here. You see these things? That's also continuum that's reflected. But the process with reflecting that is somewhat different. Some of this here, this is reflected by highly ionized gas, so it's electron scattering. And they can tell that because it's very polarized. The stuff out here, that's dust. So that's cosmic dust that's scattering that radiation. And you can see there's dust right where that knot is. I mean, this is the spatial part is going this way. So at that particular location, that gas that's making this emission of carbon-4 has dust in it. And so you can tell all that just from that one particular spectral image. So then, that gives you an idea what you want to do. There's one more thing that this is very powerful is, we know how far away NGC 1068 is, more or less, and so we can know what the scale of this is. You can see it on the sky, what the scale is, and it's a couple of arc seconds. But that couple of arc seconds translates into 200 parsecs on either side of this bright central continuum. So we know where it is, we can see ionized emission from it, we can see recombination lines. I talked about recombination lines, there's one there. Collisionally excited lines, this is one here. We can see there's dust. We can see there's some very highly ionized gas close in, making the scattering, and we know how far it extends. And we know how it's moving, all from that. But to understand exactly what the physical properties of that gas are, you have to do a more detailed model. And that we can all just see just by looking at it, if you know what you're looking at. And here is, that was in the ultraviolet, by the way. So that was from about 1,200 angstroms to about 1,700 angstroms. Here is a spectrum that goes from about 3,000 or 3,500 angstroms out to about 5,500 angstroms. The scale is a little different. It's the same region, but this is a different detector. And so the scale on the detector is different. But this extent is the same. Just the format of the detector is much wider than the other detector, but made through the same slit with a different dispersive element. This is the G430L. 430 is in nanometers what the central wavelength is for that particular grading. The 140L was 140 nanometers. So you have this. You can see the same structure here. This is the oxygen-3 doublet. I think I talked about that. That's polymer beta. There's the helium-2 again. There's some neon lines. These are neon lines out here. These are neon 5, so very highly ionized neon. This spectrum is extremely complicated. Now you can go down into more detail, just extract part of the spectrum. Now, I've talked about photo-ionization models. Why am I doing this? Why am I talking about spectra? There's no point in running models unless you have something to model. Unless you're a pure theorist, and then you can make models that you never have to test them against anything, and then you're very happy. But if you go center down on this knot, this is just this region right here. Can you see that kind of bright knot there? This is a plot of the spectrum that you get from that knot. And there are about 40 different emission lines in that knot, plus some of the continuum you can see here. And you got all kinds of things here. An extreme variety of ionization state just in this one spectrum. So here, oxygen 1, it's neutral. It's a neutral forbidden line. That's unique as a strong line to AGNs. And that line is produced in neutral hydrogen gas, or partially neutral hydrogen gas, that there is extra heating in there due to X-rays. So X-rays penetrate that gas and make the properties that cause this line to be created. That's unique to AGNs. You see some stars that have them, but you never see doubly ionized oxygen and neutral oxygen fairly strong together. That's an AGN signature because of this zone of X-ray irradiated gas behind what we'll call the Stromgren zone, which I'm going to explain to you in a few slides. There's other stuff. There's sulfur lines. This, I don't know if you can see from the back, but I think you can see that the Roman numerals here are getting larger. This is iron 11 here. This is sulfur 12, which at this point was the most ionized species ever detected in an optical or visible light spectrum of an active galaxy. And then it got rediscovered. It's amazing. I discovered it, and then it got rediscovered. And the people that rediscovered it using these data, you know who the referee of the paper was? It was me. I never reject anything. I made them cite the original reference. All right, but you see all these lines here. This is neon 5 that I was pointing out from the spectral image over there. Here in the ultraviolet, you can see all these lines. Very strong carbon 4, very, very strong nitrogen 5. This is a very interesting thing. It has to do apparently with some weird aspects of a process I was explaining to some of the other speakers earlier. And also these other lines. You can see some of them are fairly broad, like this carbon 3 line. Some are broad from motion. This is, in fact, several lines together. There's 2 carbon 3 lines plus some sulfur emission in here. And other things in this spectrum, very, very highly ionized. So what is the problem here in terms of photo-ionization model? If you have a slab or a cloud of gas at some density, some distance from the source of radiation, it's going to be some characteristic ionization and temperature is going to emit as if it was that ionization and temperature. It is impossible to get all these with one component of gas. So even though it's a very small region, by the way, the scale of these knots, 5 to 10 parsecs across, which in another galaxy, that's very highly resolved. To get all that in there, you need lots of different components. So there's a whole range of density and ionization out of that spot. And you can tell that because this spectral plot here shows you this incredible variety, things that are neutral to things that have ionization energies of up to 250, 275 electron volts, all in the same region, all in the same spectrum. You should just stop now. Just ignore it. Okay. So that's one thing you can do when you look at emission line sources, and I told you Seyfert galaxies and quasars were discovered as emission line sources. But it turns out if you look at them in the ultraviolet, you see absorption. Because what happens is, as the gas is moving, if the source of radiation is behind it, that is further away, the gas that's moving or in the way, will absorb out certain frequencies of radiation, certain wavelengths. These almost always are permitted transitions. So the ion is in its ground state, and it absorbs radiation. That radiation produces the absorption line and excites the thing to some permitted state. So the one you see very, very strongly, and you can see it in this here. What's going on with this? Pressing the wrong button. Lyman alpha. And so look at this. This is blue and this is red. Almost all the blue side of Lyman alpha has been absorbed. That Lyman alpha, the emission lines come from closer in. So these emission lines come from the broadline region. This absorption is occurring outside the broadline region. So these broad profiles have been eaten away by the intervening gas. So one of the things you can do with these models, and there's they're called UV resonance lines. These are permitted transitions. This is nitrogen 5, this is silicon 4, and this is carbon 4. This is another one. This is a type 1 Seyfert 1 called, if you don't need to remember it, but NGC 3783, it says right there. The point thing is it's a type 1, so we're seeing right down to the source of radiation, the accretion disk, in the broadline region. And so this gas that's doing the absorbent is further out. So what do? Well, you can measure by a variety of means I'm not going to go into, how much gas is doing the absorbing. And what you get is something called a column density. Basically, it's, if you just draw a line to the source, it's the number of particles per centimeter squared. All right? So it basically is a function of how dense the gas is and how much of it you're looking through. Because the density, if it's a number density, goes as dense of like centimeters to the -3. You multiply that by the length you're going through, you take out one factor of length, and it becomes centimeters to the -2, and that's called a column density. So what these people did, they don't know how to spell Seifert, obviously, is they measured column densities, and then they generated photoionization models. It's a little hard to read, but basically plots of parameters that I'm going to explain in a bit to figure out what the conditions were in these different absorbers. And these are 3 different model sets for 3 of the components that are labeled here, 1, 2, and 3. And so they were able to determine the absorber properties by doing first off measurements from spectra and then following these with photoionization models. So that's another thing you can do with it. So both emission and absorption, and that doesn't always just work in the optical and UV, it also works in the X-ray. So here are some X-ray spectra of different kinds of things. This is, I showed you this, I like it, it was part of my student's PhD thesis, but this also made you see 4151. And you can see that this is the continuum, there's absorption here, the strength of this continuum, these are different epochs, all different exposures. Changes over time, and the nature of the absorption changes over time. And to model that absorption, you make photoionization models. There is analysis software that you can use to analyze these kind of spectra that is taken with the Chandra. Both this Chandra and Newton XMM data combined on this. And so this curvature is very dependent on the properties of what's doing the absorption, because this would be a power law just going like this without the absorption there, right? And so you can do this and figure out, again, by matching the shape of this to what the effect of the absorbing is. You get that from the photoionization models, and that gets you how this curvature has changed. So it's a function, in this case, of how much gas is there and what state of ionization it's in. If it's highly ionized, it doesn't do anything. It scatters the radiation, but it doesn't make these kind of very dramatic changes in the continuum. But if it's less ionized, and you have a big column of it, and we talked about column density, this is produced by something as a column density of about 10 to the 23. If it's 10 to the 24 or more, you can't see well through it just because of Compton scattering. It's called Compton thick. So once you get the 10 to the 24. So our view towards Seifert 2 galaxies, no matter what their stuff is made of, they have columns of 10 to the 24, 10 to the 25. This is very, very big. This is almost unique for Seifert 1 galaxies to have that big a column. And we get that, we learn that from photoionization models. So again, we have the data, and we apply the photoionization models to them and determine what that column is. The other thing that goes on here is that not only is there a big column, but the source luminosity, the amount of ionizing radiation produced by the X-ray source, is varying over time. That makes the thing go up and down, but it also makes the characteristics of the absorber change. So when there's not much radiation, like in these states, the absorber is more neutral. When there's lots of radiation, so when there's little radiation, the absorber is neutral. When there's lots of radiation, the absorber, the same amount of stuff, becomes more ionized and therefore more transparent. And that's part of this change in curvature here. And you can do that by generating photoionization models for each of these individual spectra. Yeah?
Sorry, Professor, I'm a little lost. But the photoionization is the solution for variability?
No, you can look at what the cause of the variability is by generating photoionization models. So you look at the physical state of each of these epochs, and you model it with a photoionization model and says, okay, here the column of gas didn't change, but now it's very transparent because it's more highly ionized. And in this state, same amount of gas, but it's very opaque because the gas is more neutral and absorbs radiation more effectively. Is that the okay?
So Steve, one question, curiosity, what is this soft access?
This junk?
Yeah.
I don't know.
Shouldn't it be absorbed? Is it coming from?
It is absorbed, but well, this okay. Anybody want an answer? Some of this we know what it is, and there are lots and lots of emission lines. I showed you a X-ray spectrum of Seifert 2. All those emission lines are out there, and that contributes to this. In a very high state, which is none of these are in a high state, that little bit of extra radiation wouldn't show up at all. It just shows up as noise. In these lower states, and these are all low luminosity states, you can see this. And at this resolution, they look just kind of like a bunch of stuff. There is other stuff there, even in the high states, that does not appear to be emission from extended gas. That's what we don't know what it is. There's lots of models for it. It might be some radiation, blurred smeared out radiation, relativistically smeared line emission from the inner part of the accretion disk.
Well,
Nobody
the
knows.
audio would have to be after the absorption.
Yeah, in that case, here this is extended emission. But maybe some, yeah. Okay, and you can actually see it much better here. See this? You hardly can see it in this one. This down here are a bunch of emission lines. It's primarily silicon and magnesium emission lines there, all sort of grouped together. And when the thing is in a high state, they just look like noise. When you get in the low state, you can see that feature, and the breadth, the width of that feature is similar to this. This is probably neon and oxygen emission lines. Okay. This is 3783, another secret one. I showed you the ultraviolet spectrum. This is the X-ray spectrum, Chandra. And you see all this stuff there? These are all absorption lines due to gas between us and the accretion disk. And so you can see emission lines in the X-ray, you can see the shape of the continuum, but in certain states you can see all these absorption lines. This is from a paper by Caspi et al. And this is a 900 kilosecond, very, very long exposure time on an AGN. And you can see all this myriad of lines, and he identified all these different transitions from these elements. He was able to fit that with photo-ionization models and determine what the physical properties of that gas were. So now, how do the models work? Okay, so that's why we're doing it. So how do the models work individually? What you're looking at is you're looking at basically a radiative transfer problem. So you have, if you want to call it a cloud of gas or a knot of gas or some gas, filament of gas that's being ionized, the radiation from the accretion disk and its corona goes through that gas. So you can think of things that there's a face that's illuminated, that's closest to the source, and then the radiation transfers through that. And the amount of radiation is absorbed and absorbed and absorbed until you essentially run out of radiation. And that sets the physical properties of it. So here is a schematic. This is actually from the handbook for the code Cloudy that I'm going to talk about later. It shows you a very simplistic view of what it is. And so you can think of this, he's not worried about the structure. He has sort of an infinite slab going in this direction. So it really has no physical limit this way. This is the thickness of it. So that column density I'm talking about would be measured in this direction. So here is the incident radiation from whatever's making the radiation. You can do this with stars as well. It doesn't have to be an AGN. Some of it gets bounced off. It's reflected. That's the illuminated face. He calls this the shielded face. There are various ways you can do this. Inside here, radiation is created because you've excited the gases, you've ionized the gas recombines, the excited ions decay, and that radiation is produced internally and will try to escape. And then if you were back out here, you'd see this radiation that went through with all the absorption superimposed on it and all the emission that was produced inside here that gets out this way. So that's the zone. This is a very basic thing. And from an algebraic or computational standpoint, just doing this at a very basic level gives you a very simple differential equation. You start out with radiation. You use up the radiation, make a little bit more maybe, and then you're left with what's left over. Okay? Now, what goes on? See, this is the thing that really does help you, is to understand what's going on. People take things like these publicly available codes, and it's like a big black box. And they turn the handle on the box, and boom, there's the answer. But they don't know what went into it. So it's good to at least have some idea what you're doing before you do it. wish somebody had told me that when I was younger. But, you know, that's not related to science, by the way. Okay, so the simplest thing is to take a gas composed of hydrogen. This is in all the standard textbooks. And what you have here is a balance between ionization and recombination. Because if that, all you got is hydrogen, that's all you get. You don't have to worry about collisionally excited lines very much. So here is in terms of this thing called the mean intensity. That's the radiation, you know, in units of area, time, frequency, interval, and also solid angle, I think, given off by the source. That's why there's a 4 pi in there. But you're interested in this in terms of photons. So you can integrate that and get the amount of energy. But what you're interested in is the number of photons at each frequency interval, because that gives you the rate at which you can ionize hydrogen. And that's why it's divided by h, Planck's constant, in the frequency here, is part of the integration. The other thing is, this gives you how much hydrogen you started with. This is a number density, so hydrogen atoms per cubic centimeter. And this is the photo-ionization cross-section for hydrogen. So that basically has units of centimeters squared and tells you how efficiently the hydrogen atoms can absorb radiation from the ions. And you can write it in different ways. You can take this junk here and stick it all in one thing called phi, but it's the same equation. And again, this is for neutral hydrogen. And you integrate from, say, this would be nu naught, so this is 13.6 eV divided by Planck's constant. Or if you want, 3.288 times 10 to the 15 hertz. Why do I know that? And then you can write this again simply. The different ways you can write this integral, this is this gamma here. This and this are literally all the same thing. The balance here for ionization is the inverse process, which is recombination. So the right-hand side, if you finally get to the right-hand side here with all these unit steps, tells you the rate of recombination. And this is all per unit volume here, because you've got a per unit volume here. So these are electrons, and these are protons. That's all you got in hydrogen gas. They recombine and make hydrogen atoms. And this is a coefficient, the recombination coefficient for neutral hydrogen. It's a function of temperature. And I'll maybe talk about that in a little bit. And these things are all in per cubic centimeter per second. So if this is in balance, you have essentially a static nebula, gas, in equilibrium, in ionization equilibrium. Caveat, almost all these models are equilibrium models. There are non-equilibrium models of these things, but they're very difficult to test and to run. And so some time-dependent ones have been run by, they run a model and then they look at the conditions and they predict what the conditions are going to be and sometime later and they run it like that. And apparently people are working on time-dependent photoionization models now, but I don't think any are publicly available. So everything is static. There's a good reason, though, that static or things that are equilibrium might be worth modeling, because they last. If they're in rough equilibrium, they're going to stay for a while. Non-equilibrium situations are very unstable. So if you're looking at a cloud of gas that extends over 10 parsecs, you're seeing a spectrum, the thing is probably roughly in equilibrium. The thing where non-thermal equilibrium things have to be done. But at our scale, we can think everything's in equilibrium. So moving on. It's useful not to use this. And to, typically in cases where you have an unresolved source. So you have this thing here, tells you solid angle and whatnot. If you've got some extent, like a star that's actually roughly spherical, you have to worry about mean intensity. But if you're dealing with an AGN, even in the very center region where the broadline region is, you're far enough away from the source that the source is a point source for you. So you don't have to worry about its physical extent. Once you do worry about its physical extent, the whole problem becomes much more complicated. Okay, so we have this here. This is the luminosity now in ergs per second per frequency interval that the accretion disk system is emitting. And this is just the 4 pi r squared. R is the distance between your cloud of gas and the source. So it's just the radiation dilution factor. So this is a flux. And again, if you want to go back and look at what the recombination coefficient is, at like 10,000 Kelvin, which is where everything is in the universe, right? It's about 4 times 10 to the minus 13 centimeters cubed per second. And this is a useful thing because if you have this and you know what the density is, if you multiply density, number density by this, you can see you get inverse seconds. If you flip that, it gives you a rough time for recombination. So in terms of sources that vary, if you flip this thing, it can tell you what the time scale is for variation, at least for hydrogen. And you can do this for other elements that have different recombination coefficients. So this is a very useful thing to have. And the other useful thing to have here is Q. Q is just the luminosity of the source in terms of photons. Remember, we're dividing by h nu here to get the distribution of photons at different frequencies, not the energy distribution. If you integrate this, you get the total amount of ionizing photons emitted by the source. This is very important because this is one of the parameters you need to have to run a photo-ionization model. You have to have some idea what Q is. But as the source changes, Q changes. I mean, directly. If the source is 4 times less luminous, Q is down by a factor of roughly 4, depending on how the thing varies. So, this is very useful. Now, you talk about that transfer of radiation from the little cartoon that I showed. There's your differential equation. So, I is the specific intensity of radiation, which again has solid angle stuff in it that we don't need to worry about in the cases that I'm talking about. So there it goes in. So there's the rate that it changes. ds is some incremental distance into the gas. And this tells you how much is getting absorbed. So there's your ionization cross-section. There's your number density of hydrogen. And that's based on the amount of radiation you had coming in. You can see it's a negative number. So the rate of change here is giving you less radiation. Then there's this thing. This thing is the local emission coefficient. So I had that thing with those little arrows from the gas itself making radiation. It's all buried into this parameter, which is a local emission coefficient. And so this equation is what a code will be solving as it goes through. It can get a lot more complicated than this, but this is the basic idea. And as you integrate all the way through, you can see what radiation came out the back. When you run a cloudy model or any kind of model, this is what's going on inside when the model is running, is that at each position, this equation is being solved. As you like go get a cup of coffee, let the thing run, run overnight, take a nice nap, whatever. It's busily doing that and solving that equation. For the sake of completeness, though, the specific intensity has the incident radiation here and any radiation that can form in the gas. This corresponds back to that emission coefficient in the other equation. This can become very important. So one of the things that happens, is this too much detail or are you okay? It's too much detail, but you're okay. Yes to both, okay? Hey, I gave you the pictures the other day from the black holes, so now, I've drawn you into the dark world of what goes on inside a photo-ionization code. So now you'll never be the same again. Okay, so they break this. The S means stellar or source, whatever you want to call it. The D is diffuse. So you can break the specific intensity into these two parts. The diffuse part could just be like the photons are emitted by recombination and whatnot. If they don't do anything, if they're low enough energy they can't ionize anybody, then they're not really that important in this equation. But here's something that's important. The energy to ionize hydrogen is 13.6 electron volts. The energy to doubly ionize helium is 54.4 electron volts. When an ion recombines, the electron is captured at some level and just cascades down. As it cascades down, it emits energy. So if you've got a hydrogen atom and you capture the electron at the top, at the n equals infinity continuum, and you drop down, you get 13.6 electron volts. You can ionize some hydrogen and maybe somebody else, but and we'll get to what happens to that guy. If it falls to a level that's steps down in smaller increments, you don't get any ionizing radiation. The helium, however, when it recombines, can ionize lots of stuff, including lots of hydrogen. And that's one of the things that goes in to this piece here. Okay? And we can go back, not worrying about the two different pieces, but you can go back to our differential equation there and reformat it to bring the specific intensity to one side and all the other stuff on the other side, and take an integral. The integral is the distance you've gone into the gas. All right, and here it's just one-dimensional, so it's fairly simple. Most of the models for AGN, again, are one-dimensional models. So integrate this over all frequencies if you wish, and this is the distance in. You can see you've got the hydrogen density and the cross-section. Now this defines a new term that's extremely important in any kind of gas-type astrophysics, stars, and also in cloudy models, and that's the optical depth. The optical depth is this. It's given tau. Here it is a function of frequency and a position r that you've integrated into the slab. So tau at r0 is 0, because then it goes to 0. You can look at what the dimensions of tau are. It's dimensionless. It's just a number. Because you've got a number density, you've got a cross-section, so you've got 1 over length and integrating over length. So it's a dimensionless parameter that you can use. Remember I showed you those absorption lines in the spectrum of 3783? What they really actually determine is tau for those absorptions. And they can get everything else from it, because tau is related back to things like the density of the gas and this cross-section. And then, once you integrate, though, you get a very simple expression here for what happens to the specific intensity as the radiation migrates through the gas, and that is it falls off exponentially as e to the minus tau. So again, a lot of physics goes into this, but what you get is a very manageable expression, and that is something you can use when you're building a model. In fact, the earlier versions of photo-ionization codes, they started doing that for planetary nebula back in the late 1960s. Remember I showed you that planetary nebula, lots and lots of emission lines, so obviously a good thing to actually run a photo-ionization code. Geometrically simple. Planetary nebula tend to be spherical or box-shaped, and there's a star's core in the middle producing radiation in all directions, so at that level it's a fairly simple thing to solve, and lots of emission lines to look at. But they didn't really do this in terms of optical depth. They did it kind of into physical depth, into a slab of gas or a cloud of gas. That's really very computationally inconvenient. Because if you set it, I'm going to go this many, on 10 to the 10 centimeters per step, conditions can change very dramatically. And the code is looking for convergence. I'll get to that in a second. And if you jump over a boundary, it won't converge properly. Then you got to go back and change the boundary and that sort of thing. So the modern codes, like Cloudy, do their integration not in terms of R. They do it in terms of tau. Because you can look at incremental changes. I don't want tau to change by a factor of 10. So if I go from neutral gas, from completely ionized gas to more neutral gas, I can have very, very big changes in tau over a very small change in R. So they don't do it that way. They do it in terms of tau. So it's important for that reason. It makes it computationally manageable. And you don't have to keep rerunning it, rezoning it. Okay, so now, getting back to the recombination coefficient. So now before I was talking about the absorption of radiation and ionization. The other side of the equation is recombination. And you can look at it this way, and this is n equals 1 to infinity. This is just for hydrogen, for example, at some given temperature. And so this accounts for recombination to every level, defined by principal quantum number of the hydrogen atom. So